Have you ever witnessed something truly mesmerizing, like a massive swarm of fireflies suddenly synchronizing their flashes across a field? Or perhaps you've seen a huge flock of birds move as one, a single fluid entity painting patterns against the sky. It feels almost magical, doesn't it? Like there's an unseen conductor orchestrating this impossible ballet. But what if that conductor isn't some central command at all? What if it's, well, a deeply embedded universal set of physical laws that govern how all complex systems organize themselves, from the smallest cell to the largest crowd? Today, we're taking a deep dive into exactly that, the fascinating unifying world of coordination dynamics, self-organization, and the HKB model. We're going to explore how surprisingly simple, yet, profoundly universal principles can explain everything, from the intricate way your fingers move, to how your brain processes thought, how you master new skills, and even how entire groups of people coordinate their actions in a social setting. Our mission in this deep dive, really, is to give you a genuine shortcut to understanding how nature, at every scale imaginable, handles immense complexity. We're going to uncover a unifying power that bridges physics, biology, and psychology. So get ready for some serious aha moments, because this perspective is truly going to change how you see the world, and perhaps even how you see yourself. Let's start with something that seems so simple, but is in fact incredibly complex. I mean, the everyday actions we take for granted. Think about simply reaching for that cup of coffee or just walking down the street. How do the billions of cells in your brain and the countless muscles and joints throughout your body all cooperate? How do they coordinate to make those seemingly effortless movements happen? It's a question that, believe it or not, stumped even the brightest physicists for centuries.
It's a fundamental challenge, absolutely, because our intuition often tells us there must be a central commander, a little person inside pulling the strings. But this deep dive really challenges that traditional view. The idea of the brain as a static computer with pre-programmed instructions or stored content.
Right, like files in a folder.
Exactly.
Yeah.
Instead, we'll explore an idea championed by brilliant physicists like Richard Feynman. He suggested that the brain, and indeed all living systems, are far more like a constantly shifting river. In this river, patterns emerge and disappear without any external agent orchestrating them. As he put it, contents aren't contained anywhere, but are revealed only by the dynamics.
Wow. So the information isn't stored, it is the pattern.
That's the essence of it. It's a crucial shift in perspective. The core idea is that self-organization is the fundamental principle behind all structure and pattern formation. We aren't just bound by the properties of matter itself, but by these universal organizing principles that dictate how elements come together and interact.
So it's less about a blueprint being followed and more about the system itself, sort of finding its own way to organize.
Exactly. And that leads us right to the idea of a pattern. We all intuitively recognize patterns, right?
Sure, frost on a window, butterfly wings.
The delicate frost on a window pane, the intricate designs on a butterfly's wings, or the way sand ripples on a beach. But what is a pattern, scientifically speaking? It's a question that really harks back to Galileo's genius. His true insight wasn't just observing things, but abstracting the underlying unity between seemingly disparate events, like a ball rolling down an inclined plane and the majestic motions of the planets. He saw the consistent pattern in the process, not just the individual events. And building on that, physicist Erwin Schrödinger profoundly emphasized what he called order transitions as being absolutely fundamental to life. He distinguished these from the simpler disorder-order transitions that we typically see in non-living systems.
Like water freezing.
Exactly, like when water vapor turns into liquid and then freezes into ice. Those are about things getting more orderly from a less ordered state. Life, Schrödinger argued, involves far more complex processes, specifically non-equilibrium phase transitions, where one organized state transforms into another organized state. This leads us to a key concept. All structures and behaviors in animate nature are dynamic patterns, not static ones.
So even something that looks solid, like a bone?
Fundamentally, yes. The difference between, say, a static bone structure and a fluid movement is primarily just the timescales on which these dynamic patterns exist. They are all fundamentally patterns of change and organization over time.
So even what looks static is really just a very, very slow dynamic pattern that's quite a mind bender. But for these dynamic patterns to truly self-organize, it sounds like there must be some ground rules. What are those universal principles that allow patterns to emerge seemingly out of nowhere?
You're right. There are indeed specific criteria. First, systems must be dissipative and far from thermal equilibrium. Now, that sounds technical, but think of it simply. You and I are dissipative systems. We're constantly taking in food and air, using that energy, and then giving off heat and waste. We're never in a perfectly balanced, static state. Living systems are always in this dynamic flow state, exchanging matter and energy with their surroundings. That's metabolism, essentially.
So constantly feeding off their environment rather than being a closed box, like a rock that just sits there.
Precisely.
Yeah.
And second, through nonlinear interactions, energy doesn't just spread out evenly. It concentrates, much like water finding channels to form a river. This creates the specific patterns we observe. And from these interactions, special markers emerge that define the new pattern, what we call collective variables or order parameters.
Okay.
They're like the overall tune that emerges from individual instruments playing together.
So it's not just the sum of the parts, it's something genuinely new that emerges, like the pattern of a flock of birds, not just individual birds flapping their wings.
Exactly. And these collective patterns then turn around and influence the individual bird. That's what we call circular causality.
Okay.
The whole influences the parts, which in turn sustain the whole. It's a feedback loop. And finally, control parameters are continuously varied. These are like tuning knobs.
Right.
They promote instability, pushing the system to its limits, and that's what leads to the emergence of new coordination patterns.
That's a lot to wrap our heads around, but the way you've broken it down with analogies really helps. Could you give us some vivid examples from the natural world where we can actually see these universal principles in action, something we can visualize?
Absolutely. The one classic example is Bernard convection. Imagine a thin layer of fluid, like oil, heated uniformly from below in a pan.
Yeah.
If you just heat it gently, nothing much happens, just diffusion. But at a critical temperature gradient, that's our control parameter, the fluid doesn't just get hotter. It spontaneously organizes into beautiful hexagonal convection cells, like a honeycomb pattern. The fluid starts moving in these little circular currents.
Wow.
What's important here is that the same underlying mechanism can yield different patterns depending on, say, the aspect ratio of the pan, its width to its depth, which acts as another control parameter. And conversely, different mechanisms can sometimes yield the same pattern. It's not a one-to-one relationship, but a powerful demonstration of emergent form. Another remarkable illustration comes from Turing patterns. Yes, the same Alan Turing, the brilliant mathematician.
The code breaker.
The very same. Yeah. He mathematically predicted reaction diffusion mechanisms that could explain how spatial patterns form. These aren't just theoretical. They can explain the intricate patterns on animal coats, think like leopard spots, giraffe dapples, or zebra stripes.
So that's not just genetics programming spots.
Well, genetics sets up the conditions, the chemicals,
Yeah.
but the pattern itself emerges from the interaction of these chemicals, activators, and inhibitors diffusing across the skin. It's a dynamic process. They also explain things like world leaves and plants, and even the aggregation of cellular slime mold, Dictyostelium discoideum. When these individual amoeba-like cells run out of food, they send out chemical signals and aggregate into a multicellular slug, and they form wave patterns that are entirely analogous to the Bernard instability. These are all emergent patterns without any central blueprint or command. It's a purely self-organizing process.
Okay, let's unpack this and get into some truly groundbreaking research that brought these more abstract ideas right into the realm of human experience. The story of coordination dynamics often begins with a surprisingly simple yet profoundly insightful experiment, just waggling your index fingers back and forth. JPhys Kelso's pioneering work in the mid-1980s used this seemingly trivial action to uncover some truly fundamental laws of biological coordination.
That's right. In these experiments, subjects were asked to rhythmically move their index fingers back and forth. And what they found was quite striking. Subjects could reliably perform only two primary patterns of coordination. The first was in phase, where the fingers moved together side by side, homologous muscles contracting simultaneously, both up, both down.
Like clapping your hands together rhythmically?
Sort of, yes. Imagine two parallel pendulums swinging in perfect sync. The second was anti-phase, where the fingers moved oppositely, non-homologous muscles contracting simultaneously, one up, one down, like windshield wipers moving in opposite directions. The key discoveries here were, well, threefold, really. First, only these two stable coordination patterns naturally emerged. People didn't spontaneously do complex, weird patterns.
Oh, okay.
Second, and this is crucial, when subjects started in the anti-phase pattern and the movement frequency was slowly increased.
The speed they waggled.
Exactly, the speed. That acted as our control parameter, the tuning knob. They would abruptly switch to the in-phase pattern at a critical frequency, typically around 2 hertz, maybe 2.5. This sudden qualitative change is a classic example of a phase transition.
A phase transition like water boiling or freezing, but happening in your fingers. So it's not a gradual shift, but a sudden, almost all or nothing change in how your fingers are working together.
Exactly. You don't get half frozen water, generally speaking, and you don't get half switched fingers in this context. It's complete reorganization of the system's behavior once a certain threshold is crossed. And third, they observed hysteresis. If, after switching to in-phase, the frequency was then decreased, subjects did not spontaneously switch back to anti-phase.
They stayed in phase.
They stayed in the in-phase mode, even at frequencies where anti-phase was previously stable. This memory effect, this dependence on history, is a hallmark of nonlinear systems. It's like pushing a door open requires a certain force, but getting it to swing back closed might take a different amount, or it might just stay open until you actively push it back. The path matters.
It really does seem counterintuitive, doesn't it? That something as complex as human physiology, I mean billions of neurons, countless muscles, boils down to these two simple patterns, acting like a pair of simple coupled oscillators. What's the most surprising part of that for you, given the brain's complexity?
For me, the most surprising part is that this isn't just about efficiency, although it is efficient. It's a truly synergetic effect. It demonstrates that the whole system behaves in a way that's far simpler than the sum of its incredibly complex parts. You don't need a central calculation for every muscle fiber every millisecond. The system finds these stable, simple patterns on its own. And this is where the Haken-Kelso-Bunz HKB model comes in. It formally described these precise experimental observations. The relative phase between the two fingers was identified as the order parameter or collective variable.
Phi, like the Greek letter.
Yes, phi. It's a single, low-dimensional variable that expresses the information exchange between the interacting parts, the fingers in this case. It beautifully captures how the limbs are coordinated, whether they're in sync or out of sync or somewhere in between. The coupling strength between the fingers and specifically the movement frequency were identified as the control parameters. As these were continuously varied, they led to instability and the emergence of these new patterns. You can visualize this with the coordination potential, which is often depicted as a landscape. Imagine a landscape with valleys and hills. Stable coordination states, like in-phase and anti-phase, are represented as valleys or basins of attraction, where the system naturally tends to reside. Unstable states are like hilltops, precarious positions. The original HKB model showed initial B stability, meaning two stable valleys, in-phase and anti-phase. As the control parameter frequency increased, the anti-phase valley became shallower and shallower.
Less stable.
Exactly, losing its stability until at a critical point, the system switched, essentially falling into the deeper, more stable in-phase valley. Mathematically, this abrupt change is known as a pitchfork bifurcation, but the key idea is that sudden qualitative shift. And what's really key here is that this attractive force isn't mechanical, like a physical spring connecting the fingers. It's informationally based. It reflects how the parts communicate dynamically to form a coherent whole.
Okay, so we've got these patterns, in-phase, anti-phase, and we've got the math, the HKB model describing them. But how do we know this isn't just a convenient model? How do we know it's actually describing how our bodies are behaving? What are the telltale signs, the smoking guns you observed in these experiments that confirm these dynamic principles?
Excellent question. Because you're right, a model is just a model unless it makes testable predictions that hold up. And these are not just abstract mathematical concepts. They are directly observable, quantifiable measures that tell us precisely how biological systems self-organize and change in real time. The HKB model and its supporting experiments revealed classic signatures of these self-organizing, non-equilibrium phase transitions. First, there were critical fluctuations.
Fluctuations, like variability.
Exactly. As the system approached the transition point, say, as anti-phase coordination was about to lose its stability, the variability or fluctuations of the relative phase increased dramatically.
So if I'm hearing this right, these critical fluctuations are like warning signs, almost like a system wobbling or hesitating just before it's about to totally transform its behavior. Is that the aha moment here, that we can actually see a system preparing to change?
That's perfectly put. It's nature's way of signaling an impending shift. Imagine a bridge before it collapses. It doesn't just snap. It might sway more, groan, take longer to settle after a gust of wind. These fluctuations are quantifiable clues that a system is losing its current stability and getting ready to reorganize. Second, we observed critical slowing down. If you perturbed the system, for example, giving a quick, unexpected pork pulse to one finger, it took longer and longer for the system to return to its stable state as it neared the transition.
Ah.
This effect directly reveals how stability is lost. Like trying to balance an unstable spinning top, it takes longer to right itself. And third, the switching time distributions, basically. How long the actual switch from anti-phase to in-phase took were accurately predicted by the stochastic version of the HKB model, which includes noise. These are powerful empirical confirmations, not just fitting data after the fact, but predicting these specific dynamic signatures. They demonstrate how these principles manifest in living systems.
So we've seen how remarkably simple equations can explain how identical things, like maybe two index fingers assumed to be the same, switch between patterns. But what about when things aren't so perfectly matched? Real life is messy, full of differences. We have handedness. Our brain hemispheres aren't identical mirrors. Body parts might have different natural frequencies or strengths. How does this elegant HKB model handle the beautiful, imperfect diversity of biological systems?
That's a crucial point, absolutely, because biology is rarely perfectly symmetrical. The original HKB model, as powerful as it was, initially assumed identical components, like the two index fingers being clones. To address this reality, a new term was added to the HKB model, delta omega.
Delta omega, like the change in frequency.
Precisely. This term specifically expresses the heterogeneity or diversity between individual oscillatory elements, such as different natural frequencies. Maybe one finger wants to oscillate slightly faster than the other. What ONO does is it breaks the symmetry of the dynamics. Instead of a perfectly symmetrical landscape with identical values for in-phase and anti-phase, it causes a tilt in the coordination potential. This tilt shifts the system's collective states and fundamentally changes how transitions occur. For instance, instead of the clean pitchfork bifurcation seen with identical components, switching now often takes the form of a saddle node bifurcation, where stable and unstable fixed points essentially kiss or collide and disappear. This leads to more complex, often non-in-phase or anti-phase, stable solutions. It allows the model to capture a much richer array of biological realities and diversity.
And what's fascinating here, it seems, is that this less rigid, more flexible form of coordination isn't a bug in the system. It's not a problem to be overcome, but a fundamental feature crucial for how living things adapt and function.
Exactly. That's the profound insight of metastability. Even after the fixed points, those perfectly stable values in our coordination potential landscape disappear due to increasing heterogeneity or changing control parameters. Some curvature in the potential remains. The system still exhibits coordination tendencies, or ghosts, of where the stable states used to be.
Ghosts. So it remembers where stability used to be.
In a manner of speaking, yes. It means the system isn't strictly mode-locked into perfect synchronization anymore. Instead, it displays a partial coordination, hovering around preferred phase relations for a while, before occasionally slipping, losing that coordination briefly, and then perhaps reestablishing it.
So it's like a dancer who doesn't just stay in one rigid pose, but fluidly moves between them, always finding a balanced, beautiful new form. Not perfectly rigid, but not completely random either.
That's a wonderful analogy. It's a dynamic balance between integration pulling together and segregation maintaining individuality. This phenomenon perfectly aligns with relative coordination, a concept described by the brilliant biologist Erich von Holst way back in 1939. He observed this in fission movements and saw it as a latent and never-ending struggle between the maintenance tendency, where individual elements express their autonomy and intrinsic properties, like a preferred natural rhythm, and the magnet effect, their attraction to certain phase relations, pulling them into coordination. The system is constantly navigating this tension.
Wow, von Holst saw this in the 30s.
He did, purely through observation. It took coordination dynamics to provide the mathematical framework. These deep consequences of metastability are crucial for understanding the balance of integration and segregation within the brain, allowing different brain regions to be both specialized and communicate effectively. It's also vital for flexible sensoromotor coordination in larger ensembles of interacting parts, whether it's limbs or neurons or even people. It allows for both flexibility and stability in biological systems, which is absolutely vital for adaptability in a constantly changing world. Now, while the HKB model proved exceptionally powerful for understanding the coordination of a few interacting components, primarily these dyadic systems like two fingers, two limbs, it's important to note that entirely independent work was being developed around the same time by Yoshiki Kuramoto in 1984. His focus was quite different. It was on the statistical features of coordination among very many elements, thousands, millions even, The Kuromoto model was initially developed to explain chemical oscillations, actually, but it rapidly became a paradigm for understanding large-scale coordination in diverse biological systems.
Like the fireflies we started with.
Exactly like the fireflies. The mesmerizing synchronous flashing of fireflies in a swarm, the coordinated firing of pacemaker cells in the heart that maintain our heartbeat, or even the spontaneous synchronized clapping you sometimes hear erupting in a concert audience. What's interesting is that both the extended HKB and Kuromoto models, although developed independently, share a common conceptual origin in Hermann Haken's synergetics, that overarching theory emphasizing self-organization. Kuromoto's own magnum opus on this was in fact completed while he was visiting Haken's Institute for Theoretical Physics. So these ideas were clearly, in the air at the time.
So two brilliant minds coming from different angles. One focusing on the subtle dance of a few parts, the other on the grand chorus of many, but both rooted in this idea of self-organization. That's a powerful testament to the universality of these principles, isn't it? But what are the key differences? Why do we need both models? Or why is one better suited for certain situations than the other?
That's a great question, because understanding the differences helps us apply them correctly and see their limitations. One key distinction is the nature of the phase transition they typically describe. The Kuromoto model primarily captures transitions from disorder to order. Think about it. Individual fireflies flashing randomly, then suddenly pop, they synchronize into a coherent swarm. It often describes synchronization, frequently only in-phase coordination.
Okay, so random to organized.
Yes. In contrast, the HKB model describes transitions from one ordered state to another ordered state, like the antiphase to in-phase switch in the finger experiments, or even from an ordered state to a partially ordered metaskable state. This ability to switch between different types of coordinated behavior is absolutely crucial for biological systems, which need more than just simple synchrony. Another difference is how they handle noise. HKB rigorously treats fluctuations, which, as we discussed with critical slowing down and critical fluctuations, are absolutely essential for understanding how instabilities arise and drive transitions. The classical Kuromoto model doesn't explicitly incorporate fluctuations in the same way. It's often deterministic or adds noise differently. A further difference lies in the oscillator form. Kuromoto assumes simple phase oscillators, meaning their dynamics can be described solely by their phase angle. HKB, however, allows for more complex limit cycle or hybrid oscillators, and the functional forms of these oscillators and the nature of their coupling remain an active area of research.
Why does this complexity in HKB matter so much for understanding biology? What can HKB explain that the simpler Kuromoto model maybe struggles with?
This complexity matters immensely because the simpler Kuromoto equation, which Haken himself was well aware of, doesn't exhibit phenomena like multistability.
Multistability, meaning multiple stable patterns existing at once.
Exactly. The coexistence of multiple stable patterns under the same conditions, or those crucial order transitions. These are absolutely critical for biological multifunctionality and adaptability. Think about it. You can walk, or you can run two different stable gates. You can write your name with your dominant hand, your non-dominant hand, maybe even your foot if you practice. These are all different means to the same functional end, reflecting the system's ability to settle into different coordinated patterns for the same task. HKB's richness, its ability to handle multistability and order transitions, allows it to capture this inherent flexibility of life. Now, excitingly, recent work has shown how to generalize the extended HKB model to arbitrary numbers of interacting elements moving beyond just two, N-coupled oscillators. This generalization includes the crucial SIN2 term, which was missing in the classical Kuromoto model. This term is essential for accounting for antiphase coordination and the multistability observed in biological systems. So we're now starting to bridge the gap, theoretically, between understanding the dance of a few and the grand chorus of the many, using a unified HKB-like framework.
That sounds like a big theoretical leap forward. Are there any real-world experiments that demonstrate these principles scaling up to larger groups, showing HKB in action with, say, human fireflies?
Absolutely, and it's quite compelling. Think of the human firefly experiments conducted by Zhang and colleagues relatively recently in 2021. In these studies, they had groups of 8 interacting individuals. People sat at stations with touchpads and LEDs so they could see a representation of everyone else's rhythmic tapping behavior. They were asked to synchronize.
Oh, 8 people trying to tap in time.
Yes, and they found that within smaller groups, both in-phase and anti-phase coordination were dominant patterns that emerged spontaneously, with in-phase typically being stronger, more stable. This held true regardless of individual frequency differences, the diversity in their natural tapping speeds. However, when they looked at coordination between groups, while in-phase dominance persisted, the attraction to anti-phase coordination significantly diminished with increasing diversity among the individual pacing frequencies.
This fascinating experiment really brings it home, doesn't it? It shows that the core principles of HKB, including the preference for both in-phase and anti-phase, and its sensitivity to diversity, can scale up to real-world social interactions. It offers a powerful, quantifiable way to understand human collective behavior, even in these, somewhat artificial but still social scenarios. It's like finding a deeper grammar to how we move together, beyond just simple imitation or following a leader. So we've talked about fingers, human fireflies. Let's broaden our view even further now. You've seen a horse switch from a trot to a gallop, maybe, or a bird change its flight pattern midair. Is that simply about going faster or conserving energy? Or is there something much deeper going on, governed by these same underlying dynamics we've been discussing?
It's definitely something deeper. It's one of the most elegant applications of this theory, I think. For a long time, gait transitions in mammals and birds were thought to be primarily a function of metabolic cost, basically, finding the most energy-efficient way to move at a given speed.
Makes sense, right? Nature is efficient.
It does make sense, but it turns out it's not the whole story, or maybe not even the primary driver. Recent work by Granatowski and colleagues in 2018, looking across 9 different species of mammals and birds, revealed something truly profound. Animals change gaits, not primarily for energy savings, but to reduce or avoid unstable, highly variable states of coordination.
Whoa, okay. So if I'm understanding this, it's not just that a horse prefers to trot at a certain speed because it's cheaper. It's that trotting itself becomes unstable, almost wobbly at higher speeds, forcing it into a gallop simply for stability. It makes me think of trying to, run an old car too fast and it starts to shake uncontrollably.
That's a great analogy. And it's exactly right. When a particular locomotor synergy, a functional grouping of body parts working together for that gait, becomes too variable, too wobbly to meet the current demands of speed or terrain, the creature spontaneously switches to a more stable one. Metabolic cost, then, is often a consequence of this instability, not the primary cause. The system reorganizes itself to avoid that unstable wobbling, which is actually more metabolically expensive and less efficient in the long run if you try to maintain it. We see this beautifully in horses. Studies of horse locomotion reveal that energetic costs do increase for speeds deviating from their preferred gaits. But the way these cost curves overlap strongly suggests hysteresis, and the abrupt changes are strongly suggestive of a nonlinear system bifurcating into different modes, different stable gaits. Even more remarkably, experiments with mesencephalic cats with severed brainstems, so no conscious control in the usual sense placed on treadmills, still showed periods of trotting and galloping, and importantly, an unstable region where gaits switched back and forth. Had the researchers calculated the relative phase among their limbs, they would almost certainly have found the signature fluctuation enhancement effect that we've discussed, indicating the system was becoming unstable right before reorganizing into a new gait.
Even without the higher brain centers involved.
Exactly. Furthermore, coordination patterns involving multiple limbs, like a pace, trot, bound, or jump, can be represented mathematically as trajectories on a three-dimensional torus. The essential coordination information is localized to discrete regions in this abstract relative phase space, meaning specific preferred patterns emerge as stable attractors, stable ways of moving. And these principles extend even to movements within a single limb. For instance, in single-limb multi-joint movements, like coordinating your elbow and wrist while cycling them. Increasing the cycling frequency causes an abrupt shift from anti-phase to in-phase, exhibiting both critical fluctuations and critical slowing down. These are clear, direct pieces of evidence that self-organization is at play even within the nervous system controlling just one limb. We also see what's called spatial parameter control, simply manipulating forearm posture, rotating from palm down, prone, to palm up, supine, can cause bidirectional transitions between stable coordination patterns, again demonstrating a large hysteresis effect and fluctuation enhancement. These aren't just isolated phenomena, they're all expressions of the same underlying dynamic principles at work across scales.
That's incredible, these universal laws applying from whole animals moving around right down to the joints within a single limb. But if our movements are dynamic patterns, what about something as intricate and, uniquely human as speech? We effortlessly produce complex sounds, but how is that controlled? Or maybe how is it self-organized?
That's a perfect segue, because speech production is one of the most stunning examples of a complex system where many neuromuscular elements at the respiratory level, the laryngeal level, the oral level all operate on vastly different timescales, yet somehow produce a coherent, meaningful sound. Think about it. Your breathing might happen once every few seconds, your larynx vibrates hundreds of times per second for pitch, and your tongue movements for articulation can be 10 repetitions per second or more. A baby saying a simple syllable like "eh" involves coordinating about 36 muscles. So how does this complex symphony emerge without a detailed score or conductor?
Yeah, how does that work?
Pioneering work by the American phonetician R.H. Stetson way back observed that as speaking rate increased, the syllable at could spontaneously switch to ta. Later, Tuller and Kelso showed definitively that the relative phasing among articulators, the tongue, lips, jaw, velum, etc., is the collective variable, the order parameter that characterizes the stability and change. They identified this switch as yet another phase transition in a biological system. And what was a truly crucial finding, demonstrating an intimate production-perception linkage, was this. A shift in articulatory relative phase, for example, the timing change that distinguishes eep from P, was perceived by listeners at exactly the same critical phase value where it occurred in production.
So how we hear it matches exactly how it's made, dynamically.
Precisely. It implies that the relevant information for speech perception lies precisely in the collective variables, the dynamic patterns that characterize its generation. This opens up entirely new avenues for things like speech recognition by computers. Maybe focusing on these dynamic patterns is more robust than analyzing raw sound spectra and potentially for treating communication disorders by understanding the underlying coordination dynamics. And if we look even further afield, into robotics, for instance, the ability of biological systems to spontaneously recruit or eliminate biomechanical components.
Like using your shoulder if your wrist is constrained.
Exactly. Using additional degrees of freedom when initial ones aren't sufficient for a task. That flexibility would be a wonderful feature to try to incorporate into robots. It speaks to a genuine adaptability that current robotics often struggles with. And in terms of pattern recognition itself, Herman Haken, who we mentioned earlier, proposed that pattern recognition itself is a self-organized pattern formation process. Think of Johansson's famous point light walkers.
Ah, yes, the dots on the joints.
Right. If you put reflective markers on a person's major joints and show only those moving lights in the dark, a static array is just meaningless dots. But the moment that person starts moving, naive observers rapidly perceive the human form and what it is doing, whether they're walking, running, dancing, lifting something. It's remarkable perceptual completion. The application here is that knowing the relevant collective variables for coordinated motion, like relative phase, provides a low-dimensional, meaningful description for designing computer algorithms to recognize complex biological motions rather than trying to process every single pixel frame by frame. It's a shortcut to understanding intention and action from movement patterns. #6. Mind, intentions, and learning within the dynamic framework.
So, this is all fascinating for movement and perception. But what does this all mean for our inner world? If even our most complex behavior is fundamentally self-organized, where does our conscious intention fit into this picture? Richard Feynman famously said, "Mind must be a sort of dynamical pattern, not so much founded in a neurological substrate as floating above it, independent of it." That's a pretty provocative thought, a mind that isn't just in the brain, but is the pattern itself.
It is indeed, and this dynamic framework offers a way to think about that. In this view, intentionality is viewed not as a rigid program sending instructions down a chain of command, but as specific information acting on the dynamics.
Information acting on dynamics.
Think of it as an intrinsic aspect of the pattern dynamics. Your intention, say, to pick up the cup rather than the pen, acts like a specific parameter that influences the stability of different possible movement patterns. It stabilizes the reach for cup pattern and destabilizes others. It doesn't create the pattern out of nothing, but it biases the self-organizing system towards a particular outcome. This is sometimes considered the second cornerstone of biological self-organization, how internal, purposeful information interacts with and shapes the emergent patterns. It's like a subtle nudge on our coordination landscape, our potential field. Your intention makes certain valleys deeper, more attractive. It's not a master switch, but a continuous influence. We even see potential brain correlates of this, like the Brightshots potential or readiness potential. This is a slow, negative potential shift in the EEG, detectable over the scalp, that appears about 1 second before voluntary movement onset.
A second before?
Yes, suggesting the brain is preparing. This readiness potential itself is a complex spatiotemporal activity pattern, and it potentially correlates with the intention to act. Once order parameters like relative phase are identified, intentions have no meaning outside their influence on the order parameters. They are the means by which the system can intentionally sustain a pattern that is intrinsically unstable, or choose between multiple stable patterns, giving us flexibility and purpose.
And how on earth does learning occur within this dynamic framework? Aristotle said, what we have to learn to do, we learn by doing. What actually changes when we acquire a new skill? Is it like installing new software into our brains, or is it something entirely different going on?
Not at all like installing new software, no. In this view, learning is seen as the emergence and stabilization of spatiotemporal patterns. It's really an extension of the self-organization theory. It involves a continuous interplay between our intrinsic dynamics, our natural, spontaneous coordination tendencies, and the specific parametric influences, the requirements of the task we're trying to learn. A minimal conceptual learning equation would include the basic HKB dynamics representing the intrinsic part, and then terms representing the specific informational requirements of the learned pattern. Learning is likely an order-order transition, as Schrödinger suggested, for life processes moving from one organized state, maybe unskilled, to a newly organized, more skilled state. The Zenone and Kelso experiments, where subjects learned a tricky 90-degree relative phase with the finger-wagging task, beautifully illustrate this. Remember, 0 degrees in phases and 180 degrees anti-phase are the naturally stable patterns.
Right.
Subjects were asked to learn this new, intrinsically unstable pattern 90 degrees out of phase. Their performance showed what they called the Siegel effect.
The Siegel effect.
Yes, if you plot their performance variability against the phase angle they were trying to produce, it looked like a seagull's wings. In phase 0 and anti-phase 180 were still the most stable points with low error and low variability, the bottom of the wings. But nearby phasings like 70 or 110 degrees were strongly attracted toward these stable patterns, resulting in higher variability at the tips of the wings. This highlights how our intrinsic dynamics constrain learning. Your system always wants to snap back to what's natural and easy. We even see striking individual differences. Split brain subjects, for instance, show an even stronger dominance of these intrinsic patterns, limiting their flexibility in learning new, less natural patterns.
So it's like learning to walk a tightrope. Your body naturally wants to fall to one side, in phase, or the other, anti-phase, but you're actively teaching it, forcing it to stay in this unstable middle ground.
Exactly, and that struggle, that variability, is part of the learning process. But the truly crucial insight from these studies was that learning isn't just about getting better at one specific target phase. The entire attractor layout, that whole landscape of stable and unstable patterns, actually changes with practice. The newly learned pattern, say 90 degrees, itself becomes a new, albeit perhaps shallower, attractor with its own basin of attraction. It literally reshapes the landscape of possibilities in your motor system. And the learning process itself often involves phase transition processes, instabilities and reorganizations as the dynamics shift, something predicted by theoretical models and observed experimentally. It's a fundamental resculpting of the dynamic landscape, where new stable habits are literally carved out through practice. And these principles aren't confined to individual learning either. They extend naturally to social settings, social coordination. Imagine an adult walking along a beach with a small child. They aren't physically tied together, but they are informationally coupled. They see and hear each other. To stay together, they both adjust their step frequency and stride length. This isn't rigid, perfect synchronization, especially given their different natural stride lengths. It's relative coordination. Von Holst's concepts apply perfectly here too. The magnet effect, their mutual attraction to stay together, maybe maintain a certain distance or phase relationship, is balanced by the maintenance tendency, each person's individual intrinsic properties, like their preferred, comfortable stride length and frequency.
So the child might skip a step or the adult slows down?
Exactly. There's a constant flexible negotiation. The child might skip a step to catch up. The adult might slow down and shorten their stride. There's a constant dynamic interplay, not rigid control.
This beautifully shows how flexible yet coordinated behavior emerges from this interplay of individual autonomy and interaction, even in complex social situations. It's not about one person controlling the other, but a dynamic, self-organizing process where a collective rhythm emerges from individual adjustments and mutual influence. So, if our behavior, our learning, even our intentions are fundamentally governed by these dynamic patterns, what does that mean for the brain itself? the organ doing the work? Is it a static machine that computes things like we often think? Or is it something far more fluid and dynamic?
The central thesis here, the core idea emerging from this whole field, is that the brain is fundamentally a pattern-forming, self-organized system governed by potentially discoverable, nonlinear dynamical laws.
Okay, that's a big statement.
It is. It means that complex behaviors like perceiving, intending, acting, learning, and remembering arise not from specific programs being retrieved and run, but as metastable spatiotemporal patterns of brain activity that emerge from the cooperative and competitive interactions among vast numbers of neural clusters. The great unifying principle here, the promise, is that a single language, the language of pattern-forming dynamical systems, can potentially cut across molecular biology, neurophysiology, and psychology. The linkage between coherent events at different scales of observation, say from the cell membrane right up to the cerebral cortex, is by virtue of shared dynamics. What's happening in a tiny ion channel might be dynamically connected through these principles to large-scale brain rhythms. And even at the most fundamental microscale level of individual neurons and synapses, dynamic patterns are clearly at work. Consider ion channels, those tiny protein gates embedded in cell membranes that control the flow of ions, like sodium and potassium, which underlies neural firing. The Nobel Prize-winning patch clamp technique allows us to record the activity of single channels. And what it shows is these single protein channels spontaneously switching between open and closed states. It's like tiny doors flickering open and shut.
Not just smoothly opening or closing.
No, often flickering. And the durations they stay open or closed, the dwell times, often follow power law functions, known as fractal scaling. This isn't random timing. It suggests a complex, rugged energy landscape governing the channel's conformation and potentially a global cooperative process among many parts of the channel protein itself. This is synergetic self-organization at the scale of the cell membrane.
Fractal scaling sounds quite intricate. What's the significance of that for a general understanding of how neurons work?
It's significant because it implies that even at this microscopic level, there isn't a simple fixed clock or timer controlling these channels. Instead, their behavior is influenced by complex, long-range correlations in time. It reveals a kind of self-organizing memory or influence across different timescales, even in a single molecule. Moving up slightly in scale, small neural circuits, like the central pattern generators in the lamprey spinal cord that generate swimming rhythms, or the lobster's stomatogastric ganglion-controlling stomach movements, these are classic examples. They are intrinsically oscillatory. They exhibit multi-stability, can produce different rhythmic patterns, and flexible switching between patterns. They have their own internal rhythms and can shift between them, often modulated by chemicals. Theoretical models of coupled neural oscillators, models composed of simplified excitatory and inhibitory neurons, even demonstrate phase transitions, providing a potential neural basis for behavioral transitions, like the bimanual coordination switches we saw earlier. Neuromodulatory substances, like serotonin or dopamine, are hypothesized to act like control parameters, modulating the coupling coefficients within these circuits, essentially tuning their dynamic interactions and shifting the patterns they produce. Now, moving to the macroscopic level, studying the whole brain, technologies like magnetoencephalography, using screeds, superconducting quantum interference devices, allow us to measure the large-scale magnetic fields produced by the coordinated electrical activity of millions of neurons. Kelso and his colleagues conducted remarkable experiments where they recorded brain activity with MEG, while people performed that syncopation to synchronization finger-tapping task we discussed. They show that both behavioral signals, the finger movements, and the brain signals, MEG readings over relevant sensor or motor areas, exhibited strong periodicity, critical fluctuations, increased variability, and critical slowing down right before the behavioral transition from syncopation to synchronization.
The brain showed the same dynamic signatures as the behavior.
Exactly. They observed a clear phase transition in the relative phase between the external pacing stimulus and both the behavior and the brain signals. This showed a profound brain behavior isomorphism. The dynamics governing the behavior were reflected directly in the dynamics of the large-scale brain activity. What's truly paradoxical and fascinating is that brain activity, measured by phase coherence between different brain areas, was sometimes less coherent during the more stable behavioral synchronization pattern compared to the less stable syncopation. This suggests a complex, non-trivial relationship. It's not just about the brain being more synchronized for more stable behavior. It points towards a more nuanced dynamic interplay. Using mathematical techniques like Cardinal-Lev expansion to analyze these complex brain signals, the seemingly infinite dimensional system of the human brain can often be seen to exhibit a small, or at least restricted set, of time-varying global modes, or dominant spatial patterns of activity. And when analyzing the geometry of how the brain transitions between these main spatial patterns, researchers found characteristics of Silnikov chaos. This is a specific type of complex dynamics, involving a saddle focus connecting stable and unstable manifolds by homoclinic orbits.
Okay, Silnikov chaos and homoclinic orbits. That sounds dramatically complex. Can you break that down for us? Is the brain always about to fall off a cliff, mathematically speaking, or is it more like a surfer always riding the edge of a wave, dynamically balanced but ready for anything?
It's much more like the surfer. That's a great image. The key insight from identifying this Silnikov chaos type of dynamic is that the brain appears to be inherently intermittent, never actually settling into a stable fixed point or perfectly mode-locked state, but continuously evolving in the vicinity of these unstable saddle points poised on the brink. This means that the brain isn't stuck in one rigid pattern or behavior. It's constantly exploring possibilities, dwelling near certain states but never fully committing, always ready to transition to another state. This isn't about randomness, it's about a highly structured yet flexible and unpredictable exploration of its state space. It's how the brain stays adaptable, never getting permanently trapped in a single way of thinking or perceiving. Perception itself in this view isn't about the brain locking into a rigid, stable attractor representing, say, cup. It's better understood as an intermittent, metastable spatiotemporal pattern, allowing for immense flexibility and the ability to rapidly enter and exit coherent spatiotemporal patterns as the situation demands. It's a constant dynamic dance, always adaptable, always near the edge of change. And this dynamic nature extends right down to the very structure of the brain itself, its plasticity. We used to think the adult brain was relatively fixed, but we now know anatomical structures are not frozen, but remain fluid throughout adulthood. Neural representations and cortical maps, the areas of your brain dedicated to processing information from different body parts or sensory inputs, are labile, alterable by life's experiences. This is the fundamental concept known as cortical plasticity. For example, classic experiments show that after a monkey's middle finger was amputated, the brain areas representing the adjacent fingers gradually expand into the region previously reserved only for the middle finger over a few weeks. The map reorganizes.
The brain rewires itself based on input.
Exactly. Similarly, in studies on monkeys with defermented arms where the nerve supply carrying sensation from the arm was cut, the sensory map for the face expanded dramatically by 10-14 millimeters into the now silent arm area when the face was stimulated. This suggests that this dynamic self-organization and remapping is the normal way the nervous system functions, constantly adjusting based on use and input, not just a response to injury.
That's truly remarkable. Our brain isn't just adapting in terms of function, it's actively reorganizing its very physical representations. It's like a constantly remapping internal GPS system based on where we travel. And you mentioned a fascinating, almost bizarre example of this plasticity in our own body perception, something called the Pinocchio effect.
Yes, the Pinocchio effect is one of the most vivid demonstrations of this dynamic plasticity in our perception of our own body, our body schema. James Lackner did these wonderful experiments. If you vibrate a person's biceps muscle while their forearm is restrained so it can't actually move, they can feel their arm extending, even though it's staying still. The vibration mimics the signal the muscle spindle would send if the muscle were stretching. Or, if they're touching their nose while the biceps is vibrated, they might actually feel their nose stretching, getting longer like Pinocchio's.
Seriously, that's wild.
It is. And vibrating both triceps muscles simultaneously can even make people feel their waist is shrinking or elongating. These bizarre sensations are not random noise. They are meaningful interpretations of the entire stimulation context. The brain is trying to make sense of the conflicting signals, the vibration saying extend, and the joint receptors saying no movement. The perceptual representation is thus relational and highly labile, demonstrating that your very body schema, how you perceive your body's shape, size, and position in space, is dynamically modified by sensory input in real time, constantly integrating new information into good solutions or best guesses for a coherent self-perception. It's a constant dynamic construction, not a fixed map. #tagged outro.
Wow. Today, we've really journeyed, haven't we? From the simple yet profound rhythm of waggling fingers, all the way to the intricate dance of ion channels and entire neural networks in your brain. And all through this powerful lens of coordination dynamics and self-organization. We've seen how concepts like order parameters, control parameters, phase transitions, critical fluctuations, and metastability provide a kind of universal language. A language to describe how life orchestrates its incredible complexity. This applies to everything from gate transitions in animals avoiding instability, to the nuanced, self-organized sounds of speech, to how you learn a new skill by literally reshaping your internal dynamic landscape, and even the fluid, dynamically modified perception of your own body in space. It's truly eye-opening, I think, to realize that beneath the surface of all these seemingly disparate biological phenomena lies a common, elegant framework. As you put it so eloquently earlier, the brain isn't just a static computer processing information. It's a self-organized, pattern-forming dynamical system. And its evolving, coherent, yet unpredictable spatio-temporal trajectories is the mind itself. This deep dive truly reveals something quite fundamental, perhaps, that true adaptability and flexibility in living systems don't come from rigid, top-down, pre-programmed control. Instead, it seems to emerge from a state of living near instability, poised delicately between perfect, rigid order and complete disorder. Much like that surfer you mentioned, always riding the edge of the wave. It makes you wonder, doesn't it? What does this mean for our own creativity, our ability to solve problems, or even just how we navigate the ever-changing patterns of our daily lives? Perhaps those moments when things feel a little wobbly or uncertain aren't necessarily signs of failure. Maybe they're actually the system preparing for its next great leap, its next great reorganization. We invite you, our listeners, to observe the dynamic patterns in your own life, how you move, how you interact with others, how your perceptions might shift and reorganize based on context or experience. There's a hidden orchestra playing all around and within you, constantly creating and dissolving patterns. And now, hopefully, you have a deeper understanding of its incredible score.